computer issues today, so hopefully things will go well, and I've got a backup here in case we need the backup. But again, I'm Erin Wetzel, and I'm your e-coach for chemistry. Hopefully, again, it looks like all of us now have logged in correctly. That's our information down here at the bottom of the screen. So hopefully we got our login correct. In terms of our information for this evening, hopefully you read the top slide here and realized some information like for you to go ahead and download ahead of time. So hopefully you've gone ahead and done that. Let me ask quickly, oh, and Jeremy, where you do that is, if you notice over on the attendees list, so if you look in this figure here, they show in the attendees list, there's a little a box with dashes with lines across it. If you click on that, and then you can select Edit My Info, that's where you can change your name. So hopefully you can figure that out, and I'll make this a little bit bigger for a second. Nope, that's not the right way. Let me ask one more question. I asked you all where you were joining us from this evening. Also, let me ask if this is your first session. So if this is your first session, if you will just type that in. So just type in if you've attended sessions before or if this is your first session. Just type that in the chat box. Again, just asking if this is your first time joining an mNET science session or if you've attended previous sessions. All right, so it looks like we have a mix. We've got some who've attended before and some who this is their first one. So that's awesome. We're glad to have some people on for their first session, and we're glad to have some of you joining us again after having been here before. Okay, so again, in terms of information, hopefully you went ahead and downloaded some of the information here. We will work through some guided notes as we go through our session, so hopefully you have those downloaded and you can go ahead and print those out ahead of time. You will want pen and pencil and a calculator when we go through our session, so if you need to grab those real quickly, go ahead and do so. We are going to be doing some math problems when we get a little bit later on in our session. We'll be doing some actual calculations. Now, before we get into this information, I want to talk about a couple things, and I'm trying to move things around here real quick. So first I want to talk about some different ways you can stay connected with mNET. So hopefully you've checked out the mNET website and you know that there's a lot of information available to you. So this slide here talks about some information that's accessible to you on the mNET website. And what we're looking at is different ways that you can stay connected with us. So in terms of information, we do have our coaching corner, and let me ask again, has anybody checked out the coaching corner before? So give me a yes or no if you've checked out coaching corner. And again, you can type that in the chat. Yes or no, 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 no. Okay. Let me ask this. Have you gone on the mNET website and checked out the resources there? So yes or no, have you gone to the mNET LMS, Learning Management System, and checked out resources? Okay, fantastic. So we at least have all done that. Well, what we're going to do real quickly here is take a look at find the coaching corner. So I'm going to share my applications, and this is a little bit different format. Well, I'll just share the desktop, hopefully. I've got everything opened. Okay. And on your end, because I had a couple things open there, you might want to change it to full screen on your end. So up in the upper corner there, if you click on full screen, you should be able to see everything. And what I want to show you is in the mNET website. And again, I know that's a little bit small there, so I apologize that it's minimized down there at the bottom. Let's see if I can change that real quickly. So give me 2 seconds. You're seeing my screen, so you're seeing double images there. Oh dear. Got too many things open. All right, I'm going to close this one. I hope I haven't minimize too much there. All right, so let's try this. Let's go back to sharing our screen. So on the mNET LMS, hopefully this looks familiar, but you do have your information. You can log onto your different courses, and then we have this tab here for Coaching Corner. So I just wanted to show this to you real quickly. If you click, oh, I logged out. Goodness gracious. No, that's not the one I want. I logged in a while ago. All right, so in the Coaching Corner, there's all different forums, and these are just kind of discussion sections. So there's all these different available forums. We have our science forums, and I encourage you to check those out. So I'm going to go in a different one because I don't think I've signed up for all of their forums. So if we click on biology, for example, you'll find that there's some different information, and we need to join the actual forum. So if you go to Site Administration, oh goodness, no, that's not what I wanted to go. I did this last time in our session. I was prepared to show you things, and then I wasn't able to do it, and it looks like I'm doing that again. Oh, if you click on, sorry, an actual forum. All right, gang, I'm messing up here. We will come back to that later. I forget how we actually join the forums, and maybe you've already joined this one, and maybe that's why it's not working for me, but I don't want to waste any more of your time. So we will come back to that later, and I'm going to stop sharing that, and we will go ahead and get started in our session. I apologize there. All right, so in our session today, we're going to talk about several different things. I'm trying to have too many things here open at once. So we are going to go through some different information. We're going to talk about intro to reactions, and then we're going to get into some of our math, our mole and stoichiometry. So in our last session, we talked about the moles. We're going to do a review in this session. But we're going to start off with talking about the intro to reactions, and then we'll take our mole calculations a step further and move into stoichiometry. And we'll also throw in some other information and some resources as we go through that. So let's go ahead and get started. Again, I apologize for that. Not quite knowing how to show you everything I wanted to show you there, so I apologize for that. And we will go ahead and get started. Make sure you're active and participating with us this evening. We will do some checks periodically. We'll do some poll questions to make sure you're with us. So do make sure that you're active and online with us this evening. So the first thing we want to talk about is the intro to reactions. And in terms of intro to reactions, first of all, there are 5 main types of reactions. And these should be things that we're pretty familiar with, but just to review them. A synthesis reaction, if you just look at the name there, synthesis should make sense. We're taking 2 or more things, and we're going to be making one final product. So the way to recognize a synthesis reaction, again, we're starting with 2 or more reactants, and we're ending with just one single product. And always remembering that it's our reactants on the left-hand side and our products on the right-hand side. Now the opposite of synthesis is a decomposition reaction, and a decomposition reaction, we're going to be starting with a compound, and then it's going to break apart into 2 or more substances. So basically the opposite of a synthesis reaction. In a single replacement reaction, we're going to recognize this because we're going to have an element, a single element by itself. Now it may be a diatomic, it might be one of our halogens like Cl2 or Br2, but then we're going to have with that an ionic compound. And what happens is that the single element is going to replace an element from the compound, and we end up with a brand new compound over here. So here we see that A came in and replaced C, so C basically got kicked to the curb, and now we have a new compound between A and D. Double replacements look different because with double replacements we have 2 compounds on each side. So we have 2 ionic compounds to start with. They basically just switch partners. We typically say they switch cations, which is of course our first ion here. So A ended up partnering up with D, the other anion, and C, that cation, partnered up with B, that anion. We always have to have a cation and an anion together in our ionic compounds. And then our last general type is combustion. We most commonly think of our hydrocarbon combustions where we have some sort of compound that has carbon and hydrogen. Sometimes we might have something that's a derivative, might have some oxygen in it as well. When we think about our typical hydrocarbons, we then combust it, meaning we're burning it in oxygen, so oxygen has to be a reactant. And for hydrocarbon combustion, our products are oxides of each of those, so we end up with CO2 and H2O. So let's go through some practice here for the reactions below, and as we go through these, if you'll just look at, if you print out the note sheet, you can look at those in the notes, but we're just going to have you think through them and look at our different types of reactions. So think about the first one. So you don't have to write anything here, but if we think about the type of reaction here, we see we started with 2 reactants, we end with 1 product, so that's of course a synthesis reaction. And our next example, and again, just think in your head what type this is. Notice we have 2 compounds on each side. They've switched partners, so the calcium partnered up with the phosphorus and the sodium partnered up with the bromine. So since we switched partners, that is a double replacement. And you might see double replacement, double displacement. Make sure you know those mean the same thing. In our next example, what we look out for here is we have a single element and then a compound forming a new compound and a different single element. So we have that single element in a compound. We know it's a single replacement. Again, you might see that one listed as single displacement as well. In this example, we start with 1 reactant. Reactants are always on the left, no matter what the reaction looks like. We end with 3 products, so that means that that's going to be a decomposition. And another example here, again, notice we have 2 compounds on each side. They've simply switched partners. This time we're switching partners and we have a polyatomic ion in the mix with the sulfate. So that's another example of a double replacement. One more example, this time the oxygen is first, but we see oxygen, that should make something start to go off in our head. And then we have a hydrocarbon, a carbon and hydrogen compound, making CO2 and H2O. We know that this is going to be a combustion reaction. So hopefully those seem pretty straightforward to you in making sure you can identify the different types of reactions. Now the next thing we want to talk about with reactions is making sure that they are balanced. So in order to be balanced, that means we're following the law of conservation of mass, and we are balancing for our atoms. We're making sure however many of an atom we have on the reactant side, we have the same number of atoms on the product side. Now when we're describing a balanced equation, we can talk about the individual molecules by looking at the particles that are there. We can talk about moles of substances, or we can talk about atoms, but we're not actually talking about the grams there in terms of looking at describing the actual reaction. So for example, if we looked at this scenario and we go ahead and balance it, we'll need a 2 on the product side. So notice we had the 1 carbon, we have 4 hydrogens. So in order to get 4 hydrogens on the product side, we're going to put the 2 in front. Whatever we add in terms of coefficients multiplies through for that compound. So the 2 times the 2 is going to give us 4 hydrogens on the product side. That's why we balance out there. Now we notice that on the product side we have 2. This distributes through to the oxygen here as well. So 2 oxygens plus another 2 means we have a total of 4 oxygens on the product side. So we're going to add a 2 in front of the oxygen on the reactant side in order to get 4 oxygens. Remember, whenever you add in a coefficient, it multiplies by any subscripts, and that coefficient distributes through to everything in that compound. Now in terms of describing things here, we can talk about that we have 1 molecule of CH4, 2 molecules of O2, forming 1 molecule of CO2 and 2 molecules of H2O. Or we could describe that all in terms of moles, just repeating the same thing but in terms of moles. So 1 mole of CH4, 2 moles of O2, 1 mole of CO2, and 2 moles of H2O. Or we could discuss atoms like we just did, saying there's 1 atom of carbon, 1 atom of carbon, 4 atoms of oxygen, so forth and so on. But we can't describe it in grams. It's not like we can say that there's 1 gram of CH4, 2 grams of O2. We cannot describe it that way. For the reactions below, balance and identify the type. So let's look through some scenarios here. So again, having you think through. You don't need to type anything in. So look at that type. So the first thing we're going to do is identify the type of reaction, and we're also going to balance. So balancing is just kind of a back and forth trial and error. We might notice off the bat that we have 3 chlorines here, so we can add in a 3 in front of the LiCl. Now when we add that 3 there, that means that we also added 3 lithium. So we have to add a 3 in front of the lithium on the reactant side. Type here, single element, and a compound means it's a single replacement. In our next example, we have C2H6 plus O2, so this is a combustion reaction. Sometimes with combustion reactions, we start off by doubling the hydrocarbon, but we can just kind of play through it and see what works. And as we start to work through this, we'll put a 2 in front of the C2H6. Again, that's where I typically start. That means then we have 4 carbons, so we're going to put a 4 in front of the CO2. Now the 2 here in front of the C2H6 means we have 12 hydrogens, so I'm going to put a 6 in front of the H2O. And then if we add up the total oxygens on the product side, 6 oxygens here, plus another 8 here, means a total of 14. 14 divided by 2 means I will need a 7 in front of the oxygen there, and that is now our balanced equation. Combustions can be some of the trickiest to balance. And again, we've already mentioned the type. This is, of course, a combustion reaction. In our next example, this is a double replacement, and the trick with double replacements is to balance your polyatomics as a group, or just whenever you have polyatomic ions, make sure to balance them as a group. So instead of taking our ammonium here and splitting it into nitrogens and hydrogens, 3 in front of the NH4OH. When I added this 3 here, I now have 3 of the ammonium group, but I also added 3 of the hydroxide group. So to get 3 of the hydroxide group, which is over here on the product side, I'm going to go ahead and put a 3 in front of the HOH. That also gave me 3 of just my hydrogens, which balances out my 3 hydrogens that are by themselves with the phosphate ion on the reactant side. So whenever you have those polyatomics, again, it's easiest to balance the polyatomics by keeping them as a group. And as we mentioned, that type is double replacement. One more example. This one should be very simple in terms of type and balancing. But for balancing first, we notice we have 1 rubidium here, 3 rubidiums on the product side. So we're going to add a 3 in front of the rubidium. That's all we need to do for balancing. Type, we have 2 elements coming together to make a compound. So that is synthesis. Not hand raised. Let's try something different. Give me a green check. And that same scroll down menu, just click on the little arrow down next to the figure with the hand raised, and you can do a green check. And we're getting some great green checks there. Looks like we're doing well. If you have any particular questions, if you'll give me a red X. So green check if you're okay, red X if you have questions. All right, I'm not seeing any red X's, so it looks like we are good. Oh, we got a red X there. Do we have a question? If you have a question, you're welcome to type it into the chat box. And I'm going to go ahead and clear those, your status. It looks like Debony is typing. Debony, what might be happening is it opens in a separate browser window. So whenever you try to download something from one of our sessions, you might need to look in other browser windows that might be opened up in the background. So click on your browser icon wherever you have it on your screen. I'm using Firefox, for example, so I just need to click on another window of Firefox, and that's where I can see what's down, where it's asking me to download. But it pops up in a separate browser window. Okay, I'm not sure what's going on. So we'll be okay without the periodic table. Thanks for letting me know, Chris. I'm not sure what's going on there, or Christopher. Okay, we're going to do some practice poll questions. So I'm going to go ahead and open the poll, and when we go to vote, you're going to click on the radio button, which is over to the left of the letters. So let's look at our first poll question, and our first poll question says, consider this reaction. What type of reaction, or which type of reaction does this equation represent? So you can go ahead and click on the radio button, go ahead and vote in your answer, just to make sure you're with us and making sure you're understanding what we've talked about so far. Now we've got a mix of answers here, so make sure we pay attention to what we have. Notice we're starting with 1 reactant, and we're forming 2 products. All right, so let's see how we did here. You should be able to see your results there. The majority did go for the correct answer. So when we have 1 reactant and ending up with 2 products, that is in fact going to be a decomposition reaction. Notice for decomposition, we don't have to form elements. We can form different compounds. But the fact that we started with 1 reactant and ended with 2 separate products, that means it is going to be decomposition. So the correct answer there was B. Good job to the majority who selected the right answer. Okay, we're going to go ahead and look at our next question. And right now it's going to be broadcasting, so let's clear that off. What coefficients are required to balance this equation? And if you have a question like this, if you're taking a licensure test, for example, just go through them and try them. See which one works. So take a second here, go back and forth, and see which set of coefficients there are required to balance the equation. So hopefully we're doing some back and forth, testing things out there. I've got 2 votes so far. All right, so we've got a mix of answers here. And again, like I said, the best thing to do in terms of tackling this is just to try things out. So as you start plugging things in, if you start with letter A, then you would just start trying to plug in a bunch of 2 here, and then I would end up putting a 3 here, and we can see right away that that does not work, because a 2 here would give us 4 irons, and a 3 here would only give us 3 irons. So we can go ahead and eliminate A. And you can start with one element and see if it works. Let's try the 1, 3, 2, 3. So if we put a 1 here, then that means that from the iron we would put a 2, and that would work for balancing the iron. We're going to put a 3 in front of the CO, which gives us 3 carbons. We're going to put a 3 in front of the CO2, which gives us 3 carbons. Now let's check our oxygen. So 3 times 2 would be 6. Over on the reactant side, remember we put a 3 here, plus another 3 would give us 6. So yes, the correct answer choice here is B. You could test out the other options, but those are not going to balance out your irons in particular or your carbons as you work through those. So it's going to be the 1, 3, 2, 3 is what helps us to balance out our equation. Now what we're going to talk about next is I'm going to share some classroom material. So I'm going to open up a separate file pod. And let's talk about some of the classroom resources that we have available for you here. We've got a few files, so 4 files there that are available for you to download. If you go ahead and download them now, remember it's going to open in a separate browser window. I will share these again later at the end of our session, so if you don't get them now, you can certainly get them at the end of the session as well. So we just have different practice exercises that I've used in my classroom, and I just want to share those resources with you. The first one is called Balance Buffet, and that's kind of a fun worksheet that the kids can work through. They're trying to get a total number of points, but they can pick different things. So there's certain questions for balancing that are called appetizer questions, and those are worth less points. And it works all the way up to our dessert questions, which are worth the most points. And again, they're trying to accumulate a certain number of points. And it also means if they want to try the more challenging ones, they don't have to do as many problems. And so it's kind of something you can do in the class. The students come up and show their answers, and they work through that. A lot of individualized learning as well, which we know is a big keyword these days, because students can kind of tackle things at their own pace and pick their own types of questions. So if they're having a harder time, they can start with the easier questions. If they're feeling good about balancing, they can move on to the harder questions. We have a lab activity there, percent composition of pennies lab. So what we're looking at there is a single replacement reaction. You actually are defacing pennies, so that might be a little bit of a concern. But it's a pretty cool reaction because modern pennies are basically a kind of like an M&M, but with metals. So in the middle is zinc, and then there's the candy coating is our copper that's on the outside. And if you can expose that zinc and then react it with hydrochloric acid, you can actually just end up with just the shell. The copper doesn't react with hydrochloric acid, but the zinc does. And so you can have the students write the reactions and do some pretty cool calculations in terms of looking at the actual composition of a penny. Types of reactions lab, got 2 scenarios there. So one is the actual lab for the students to work through. And the other one, I set this up as a station activity, so we know that a lot of times we might be struggling to have resources in our lab. one experiment at one station and then they're moving to another one. So it helps to conserve on resources there and also setup time. You're not having to set up 10 different stations with 8 different lab activities. You just set up those 8 stations and then the students move through those. So you've got one set of instructions and then the lab sheet that the students would fill in as they work through. Now, Dan, if you didn't quite get these downloaded right now, I will share this later in our session as well. But that is it for this PowerPoint. Oh, no, actually, sorry, we're going to keep going in this PowerPoint. So the next thing we're going to move on to is the mole review. So just by a show of hands, how many of you were with me in our last chemistry session? Was anybody in our last chemistry session? So if you were, go ahead and give me a hand raise if you were in the chemistry session that we had a month ago. Nobody was with us in chemistry last month. Okay, well, we talked about the mole last month, and so we're going to look at a review of that real quickly before we move on to our stoichiometry. So just reviewing what the mole is, you might already have a notion in your mind, but a mole overall, it's just simply a word that represents an amount when we're talking about the mole in chemistry. And in terms of that amount, it can be related to several different things. So we're not going to relate it to just one particular thing. We can actually relate it to several different things, and we're going to talk through what we can relate that mole to. So the mole can be related to 3 different things. We said it can be related to mass, and when we're talking about mass, we're going to use the actual unit of grams. And what we'll do is we'll just simply use the periodic table, and we'll use the mass from the periodic table. And that's the mass in 1 mole of a substance. And that's called the molar mass. We can also relate the mole to the number of particles, and different things that are examples of particles would be atoms, molecules, and formula units. Molecules if we're talking about molecular compounds or things that are covalently bonded. Formula units if we're talking about ionic compounds or things with ionic bonds. And our particles is going to be a set number. It's Avogadro's number. There are 6.02 times 10 to the 23rd particles in 1 mole of a substance. And then we can also relate to volume in liters. This is only for gases at STP. This is one of the most common mistakes that students will make. They'll try to use this conversion with solutions as well. When we start to talk about molarity, they think about moles per liter, and they'll try to throw this conversion factor in there. But this is for gases at STP, which is standard temperature and pressure. And we have a set relationship as well that it's 22.4 liters in 1 mole. So in terms of our relationship, it's nice to have a nice visual representation, so I encourage you to use something similar with your students if you're teaching your chemistry concepts. But we can do our relationship here. So 1 mole is equal to 22.4 liters. Again, just a reminder, that's for gases at STP only. We can relate a mole to particles, and we use our Avogadro's number, 6.022 times 10 to the 23rd particles. That's how many particles are in 1 mole of a substance. And then in terms of mass, we simply use the molar mass, which we get from the periodic table. Now, if it's an element, we just use directly what we get from the periodic table. If it's a compound, we have to add up the masses of everything that's in that compound to get the molar mass for the compound. Now, we can do some conversions, and this is what we went over in our last session. You can always access previous sessions. There's the recordings available on the mNET website. So do make sure you check those out if you need to go back and see previous sessions, or if you're preparing, for example, for an upcoming exam, make sure that you go and check out the sessions that you are struggling with. So let's look at a practice problem here. It says how many grams are in 4.53 times 10 to the 25th molecules of water. So think about our conversion here. We're trying to start with molecules, which is the type of particle, and we are converting to grams, which is our mass. And I did go ahead and give you the molar mass here. So again, we couldn't get the periodic table open, but at least we have our masses available. So let's think through what we need to be doing in terms of our conversion. We are going to be going from particles to mass, and we don't have a direct conversion here at the bottom, so what we're going to have to do is we're going to start with particles. Our first fraction will convert us to moles, and then we'll use a second fraction to convert to mass. We're going to be using fraction conversion factors as we work through this, and it's very important that your students set problems up this way, because in terms of then moving on to stoichiometry, they're going to need to set up those conversion factors. So even when you start chemistry to begin with and you do basic conversions like metric system conversions and English to metric conversions, just to get them practicing with their conversion skills, encourage them to set up those conversion fractions, because they'll continue to use those skills as we keep working through our chemistry. So again, we're going to go from particles to moles to mass. So we'll have 2 fractions. We start by writing down our given, the 4.53 times 10 to the 25th molecules of H2O. The first thing we're going to do is convert to moles, and we'll use our 6.02 times 10 to the 23rd. Now, in setting up these fractions, we always want to make sure that we give the unit and the substance. So this is how many molecules, which are a type of particle, are in 1 mole. And notice why we set this up the way we did. It allows our molecules to cancel out. We always make sure that everything cancels out as we are setting it up. Then we're going to go ahead and convert to grams. Notice this fraction. One mole, so that is the molar mass. Notice the moles are on the bottom, so that they will cancel with the moles here. So think about canceling out your units. Molecules and molecules cancel, moles and moles cancel, and we're just left with grams of water. Math-wise, we're multiplying across the top, dividing by the bottom, and I would encourage you when you do this on your calculator, put these numbers, the scientific notation, put them in parentheses. That will help to avoid any problems with order of operations on the calculator. But sometimes you might get a funky answer. Again, if you use parentheses, that should help. Start to think through and start to guesstimate the type of answer you should get. So if we're taking a number that's 10 to the 25th and a number that's 10 to the 23rd, those are going to even out so that we end up with a 10 to the 2nd in the numerator. So start to think about your answers. If you end up with a 10 to the 48th, we know we've done something wrong. So we punch that in, we end up with an answer of 1360 grams of H2O. In terms of sig figs, if you're working with your students in sig figs, for conversions, however many you start with is how many you end with. So we started with 3 sig figs, and we end with 3 sig figs. So we did some of these in our last session, so hopefully we're pretty much so up to speed on our mole conversion. So now it's time for you all to try some. Again, hopefully you have your pen and pencil and also a calculator handy, because you'll need those if you need to. Otherwise, you can try to do some guesstimating as you're working through and trying to estimate an answer. But let's look at our first practice poll question. I'll give you guys a little bit of time to work through the calculation. I'm going to go ahead and open our poll question, so it's open when you are ready to vote. But let's talk through a little bit what we're going to need to do. So before you start punching away there, we're asked how many liters at STP are contained in 4 times 10 to the 24th molecules of H2. So we're going from molecules to liters. So let's look at our mole roadmap. We're starting with a particle, and we're trying to go to volume. So think about your fractions. We're going to have 2 fractions, particles to moles, and then to volume. So start thinking about that. I'm going to go ahead and switch back to our actual problem page. You might want to jot those numbers down. So here's our actual problem. There's the molecules you're starting with. So I'm going to give you about a minute to try to punch that in and work through All right, so we've got lots of voting going on, which is great. Hopefully we've been working through and doing our calculations there. So we've got a majority going for one answer choice, going for C, so let's see if we are correct. So let's think about our math here and what we need to do. We're going to take our given information, which is the 4 times 10 to the 24th molecules of H2. Well, then first thing we're going to do is convert that to moles. So using our 1 mole over 6.02 times 10 to the 23rd molecules, we see that our molecules cancel out. And then we'll go ahead and convert to liters using that 22.4. Multiply across the top, divide by the bottom. A 10 to the 24th divided by a 10 to the 23rd should be 10 to the 1st. So we want to make sure we don't get anything like, again, 10 to the 47th or something. And then we work through our math. We get 149 liters. And if we look at our answer choices, that is, in fact, answer choice C. So great job in terms of working through that calculation. Awesome job. We're going to look at another problem. So let's start to look at this one. How many molecules are contained in 73 grams of H2SO4? So start thinking through what you might need to do. You will have the masses, and we'll come back to this, but let's think about what we're doing in terms of our actual calculations. So you're going to start with a mass, and we're asked to go to particles. Molecules are a type of particle. So again, think we're going to do 2 steps. We're going to convert from mass to moles, and then moles to particles. Think about your number here, the 6.02 times 10 to the 23rd, and I give you the molar masses. So let's go back to the actual problem. Again, I'll give you about a minute to work through that, and then we'll compare our answer for that one. I feel like we need some Jeopardy music here, so we have a countdown, or I need a little countdown timer for us. We got some great voting going on. I think for time purposes, let's go ahead and stop our voting where we are. You're still calculating, go ahead and continue punching away what you are, but let's think about our math setup here. So again, we're going to take our given, which is the 73 grams. First thing we need to do is convert that to moles, so hopefully we added up the molar mass of H2SO4, so the mass of 2 hydrogens plus 1 sulfur plus 4 oxygens. That gives us a molar mass of 98.086 grams. That's how many grams are in 1 mole. We'll then go ahead and convert from moles to molecules using our 6.02. Be careful with your math, multiplying across the top, dividing by the bottom. We should be looking for a pretty big number, so when you punch that in the calculator, particularly if you're using a TI calculator, it'll say the number and then it'll say E24 or something along those lines. The E means the times 10 to the whatever exponent. So make sure you're reading that carefully on your screen. When we punch that in, we get 4.48 times 10 to the 23rd. And again, that way that might have been written on your screen was 4.48 E23. That means times 10 to the 23rd. If we look back at our answer choices, that is answer choice D, which we had, I guess we could call that a majority. 2 out of 4 that voted went ahead and selected answer choice D. So great job in terms of working through those practice problems related to moles. The next thing that we're going to go ahead and talk about, and I just gave this as a note for myself, is we're going to talk about pre-assessment. So if we've noticed our strategies for the month, we have a monthly strategy in our science sessions, or a monthly kind of general classroom strategy. And so our strategy for this month in science is pre-assessment strategies. So what we're going to look at is talking a little bit more information about pre-assessments in general. Now, how many of you, let's do a yes or no, how many of you use pre-assessments in your classroom? So just type in the chat box, yes or no. Do you use pre-assessments in your classroom? Fantastic. Well, I bet you guys are all pretty much so experts, so hopefully I can give you a little bit of extra information here this evening, or give you some ideas you maybe haven't thought about before. But just making sure to review and understanding kind of what a pre-assessment is. It's a way to determine what students know about a topic before it's being taught. So we're just trying to get some background information and figuring out what students know. It kind of helps to guide us so that we don't teach them something that they already know. So what should pre-assessments be used to do in order to give us information for working in our classroom? They should be used to make instructional decisions about student strengths and needs, determine flexible grouping patterns. So sometimes we like our students to do group work, and by seeing how they do in the pre-assessment, then we can group them into the appropriate groups. And then determine which students are ready for advanced instruction. As I mentioned before, we're doing a lot with individualized learning these days, so making sure that we are challenging our students, and those who are ready for something advanced, we want to go ahead and give them those advanced assignments. So hopefully, again, we've used our pre-assessments for some of these different types of things in terms of planning in our classroom. It also just gives us a good general knowledge about student information and student learning, what they've learned so far. We know a big issue that we see in our science courses is that a lot of times students end up with misconceptions, and then those misconceptions kind of stick with them. And so we can identify some of those misconceptions by using our pre-assessments. Whoops. So first of all, some general strategies, and I've got a little bit of out of order here on my PowerPoint file. I apologize. So first of all, we need to make sure we decide on how we're going to use the pre-assessment. So we're going to do a pre-assessment at the start of a unit, which is a great data tool in terms of getting a baseline, seeing what students know at the beginning of a unit, and then doing similar questions on the post-assessment, or that final culminating test, to see if students have learned the information. So we might do a unit pre-assessment. We might just do a general course pre-assessment, so students come in at the beginning of a course, seeing what they know from previous science courses. Or we might also do just kind of a daily pre-assessment. And daily pre-assessments might be something that's very short, just a one question little assessment to figure out what students know for what you're going to be learning in that lesson on a particular day. So lots of different ways that we can incorporate our pre-assessments. Key thing is to keep it short. We do, especially if we're using it on a daily pre-assessment, so we want to keep it to a minimum so it's not taking up a bunch of our class time. But a lot of times this can be, for example, we call it a bell ringer sometimes if we're using it on a daily method, just to kind of figure out what students know, and we can kind of get a quick idea of how the day is going to progress. Also encourage you to mix it up. So sometimes we get stuck in a rut with our teaching, and I know it's hard when we're new teachers and we're doing so many different things, and we can just kind of get in a rut where we just kind of do the same sort of thing. We always give a multiple choice quiz, or we do things the same way. I would encourage you to just try to mix it up, even if it's just a little bit of mixing up, just trying to keep things a little bit different in the classroom. It will help to keep your students more engaged, keeps them on their toes more, and it'll make things a little bit better for you as well. You're not going to be stuck in that mundane situation where you're always doing the same thing. And then also make sure that we are using the data. So make sure when we're gathering that data that we actually use it. If you're taking the time to gather it and get some information, make sure you apply it in the classroom. So if we are going to set up different groups and do differentiated instruction, make sure that we're using that data to do so. So do follow through with it. Now in terms of pre-assessments, we do have different types scenario where we're asking specific content-based questions. We're really trying to figure out what do the students know from their previous courses. And again, this might be like our typical paper and pencil quiz. Just to throw out a couple of science examples to help you think about how this would be relevant in the science classroom. If you asked your students, for example, in a biology class to draw and label a food chain, including plants and animals, that might be a quick pre-assessment tool if you're getting ready to work with food chains or ecosystems overall and trying to figure out if students have an understanding of what a food chain is. You could ask them to draw it, and then you get some kind of background information. Or even if you ask them a simple definition. Again, this could be a start to the classes one day. If you're going to start into stoichiometry for chemistry, maybe you ask the students to jot down on a piece of paper, what does the word stoichiometry mean? And see if they have any idea. You can kind of get a background information to see if they know something about stoichiometry to begin with. Or maybe you're using this day. So it's another way we can use our pre-assessments to see if they retain that knowledge from a previous lesson. We also have some of our pre-assessments that are more skills-based. So this focuses on students practicing an actual skill as opposed to your rote pen and paper quiz, for example. They might still have paper and pencil involved, and they might still be content-based, but we're typically trying to have students do a little bit more or testing out their skills. So a couple of examples to get you thinking about what these might be. If you ask students, for example, to create a scatter plot with the data listed in a given table. So you're trying to see what their graphing skills are like. We know that students have been learning graphing for a long time in their math and science classes, but when they come to us, they might not have the best graphing skills. So this could be a quick way to assess, do they have the skills they need to successfully create the graphs that they need to create in our class. Or asking them to draw pictures. So for example, if we're going to talk about a bonding concept in chemistry, asking students to draw a picture to demonstrate covalent bonding. Again, you could do this before they learn about covalent bonding, or you could do it the day after to see if they retain the knowledge from the previous day. We also have different types of pre-assessments that are more active, so I encourage you, like I said, to mix it up, get students up and moving in the classroom. So different examples of this would be again, we're looking at having students physically moving around. One example would be 4 corners. So if you set up your room, you put the letter A in one corner, the letter B in another, the letter C in another, and the letter D in the 4th corner. You're doing basically a regular quiz, but instead of having students write it on paper and with paper and pencil, you're actually having them get up and move around the room, which can definitely help with students if they're getting a little tired. You could do a quick 4-corner assessment just to see how things are going. So again, you're just asking a multiple choice question, and they go to the appropriate corner. Graffiti wall is another idea. Maybe you have a big piece of paper up on the wall and you have students draw pictures related to the topics that you're talking about. So it allows students that like to express their creative side or trying to give some ideas of different information that they know about, just because it's a different way to express themselves and having students get up and physically move around. Yes, no cards. You can have students just have a card that says yes and a card that says no. And so again, it's kind of a general question type thing where the teacher is asking the questions, but instead of students just doing it on paper, they can actually hold up the cards. And it might be a quicker way for you to assess, just quickly scanning around the room and seeing how students are doing, whether they understand the information. So it just can be a quick assessment tool to figure out if they're understanding what's going on. So just a little bit of information there on pre-assessments. Again, I'm so glad to see that so many of you use pre-assessments in your classrooms. Hopefully we gave you a couple of additional ideas there to think about as you're starting to use more and more pre-assessments and making sure that we're using them to their full potential. So again, I'm so glad to see that you guys are using pre-assessments already. What we're going to do now is get back into our science, and we're going to talk about stoichiometry. So we've talked about reactions, we talked about mole conversions, and we're going to put those two things together and talk about what we call stoichiometry in chemistry. Now, stoichiometry, it's kind of a funky sounding word. It's just a way to relate amounts of different substances in a chemical reaction. So let's say we have our chemical reaction, we have reactants and products. We can relate those reactants and products to one another using stoichiometry. So what it comes down to is if you were given an amount of reactant or product, you can then do some math, which the math is called stoichiometry, to solve for the amount of any other substance in the reaction. And it could be that we're starting with grams and ending with grams, or we could use any of our mole conversions that we talked about. That's why it's important to do our mole conversions first, making sure that you and the students understand mole conversions, and then we can move on to our stoichiometry. Now, what do we need to be successful in terms of carrying out a stoichiometry problem? Number one, we need a balanced equation. That's why we talked about equations to start off our session tonight. Another thing that we'll need in our actual math is we will need the mole ratio. This is going to be one of our conversion fractions, and this is what truly makes it a stoichiometry problem. It's really not stoichiometry unless we have a mole ratio. That's why we're calling this the heart of stoichiometry. And then lastly, we need to make sure as we're working through the math, we use the units and we write the substances to make sure we're keeping track of everything. and tracking that everything cancels out as we work through the problem. Now again, I like to use a visual with this to help students understand what we're doing. So you see the visual that we talked about in our previous PowerPoint is tying in here, but instead of having one mole roadmap, we now have two. And we're going to have two because we're going from substance A to substance B. Again, we're taking information about one substance and relating it to another. Now the way we approach this is we're just going to figure out where we're starting and where we're ending, and that's going to help us figure out how many fractions we need as we move through. So let's say, for example, we're doing a mass to mass conversion. And then we'll go ahead and convert to mass of substance B. So you can see kind of how we piece through things and how we put our conversion factors together. But again, we're relating between two different substances. So we're starting with the first substance. The way we switch between substances is with our mole ratio. And then we go to whatever unit we want to end with that second substance. So let's go ahead and look at an example problem. How many grams of aluminum are needed to produce 15 grams of iron from the following reaction? So think about what we're trying to relate. We're trying to figure out information about aluminum, but we're starting with information about iron. So we're told that we have 15 grams of iron. How much aluminum would we need? Now remember, one of our things we need to do a stoichiometry problem is we need a balanced equation. So as we look at this equation, we clearly see it is not balanced. So before we move on, we want to make sure that we go ahead and balance our equation. And I thought I had done that, but I guess we don't have it in here, but we can just talk through. We would need a 2 here and a 2 here in terms of balancing that. Let's think through what we're doing. This is a mass to mass conversion, so we're going to start with mass. We'll convert to moles. We'll use our mole fraction, mole ratio, which will get us to moles of substance B, and then we'll convert to grams of substance B in terms of working through our calculations. So again, I'm sorry I don't have my 2's in there for balancing. We start by writing down our given, 15 grams of iron. Step 1 is to convert grams of iron to moles of iron. So notice that I'm going to make sure to include the units and the substance as we work through this. So 1 mole of iron has a molar mass of 55.85. Now that we are in moles of iron, we are ready for our mole ratio to relate between the two. And this is what it should be from our balanced equation. There are 2 moles of aluminum for every 2 moles of iron. We look at where we're canceling out so far. Grams of iron, moles of iron have all canceled. If we stopped our problem right now, we would be in moles of aluminum. We don't want moles of aluminum, we want grams of aluminum. So our last fraction here is going to be converting to grams of aluminum using the molar mass of aluminum just from the periodic table, which is 26.98 grams. $15 grams of iron. Again, this is our stoichiometry. The only way we can relate from one substance to another is using that mole ratio. We get our mole ratio from the balanced equation. So again, there should have been a 2 in front of the aluminum and a 2 in front of the iron to have that balanced. Let's look at another example, and the only way these differ is depending on what units we're starting with and what units we are ending with. So this one says what volume of hydrogen, we're told we're at STP, can be produced when 3.25 moles of zinc react with hydrochloric acid. So in terms of thinking through what we're doing, we're starting with moles of one substance, and we are then ending or trying to go to volume of the second substance. So we're actually starting here with moles. That means that right off the bat, we are ready for our mole ratio. That will convert us to moles of the second substance, and then we'll convert from moles to volume of our second substance. So this one's actually only going to have 2 conversion fractions. So again, for balancing, it doesn't look like I wrote it in for this one either. We need a 2 here to balance it out. We'll take our 3.25 moles of zinc. Since we are in moles, we'll go ahead and fill in our fraction here. So 1 mole of H2 to 1 mole of zinc. That's just a 1-to-1 ratio. Even though it's 1-to-1, you still need to show it because this is how we are converting from one substance to another. We don't want moles of hydrogen. We want liters of hydrogen, so we use our 22.4. Multiply across the top, divide by the bottom, we get 72.8 liters of hydrogen gas. One more example here. How many grams of iron 3 oxide are needed to completely react with 3.65 times 10 to the 25th atoms of aluminum? And this time I've actually got our balanced equation for us. So let's think about what we're doing. We are starting in atoms of aluminum, so we're starting here with a particle. Step 1 will be to convert it to moles. Then we'll use our mole ratio to relate between the substances. It takes us to moles of substance B. And I forget offhand, I think we're going to grams, but I don't remember off the top of my head. So we'll have to look back and see how many grams, right? Then we'll go to grams of our iron 3 oxide. Start by writing our given. We're going to convert that to moles using the 6.022 times 10 to the 23rd. Then we'll use our mole ratio to relate between the iron 3 oxide and the aluminum. We don't want moles of iron 3 oxide, we want grams, so we will use the molar mass, which we can add up from the periodic table. We got this number by simply adding up 2 irons and 3 oxygens. Multiply across the top, divide by the bottom. Watch out for our numbers here with our scientific notation. And we should get 4,840 grams of iron 3 oxide. All right, so now it's time for you guys to do a couple practice poll questions. I think we'll have time for about one poll question here, and then we'll go ahead and wrap things up for our evening. So let me go ahead and get our poll set up here. Let's start to look at our problem, and then I'll go ahead and open the poll while you're working. If 55 liters of ammonia reacts with excess oxygen at STP according to the reaction below, what mass of nitrogen monoxide will form? Now notice we've got some extra information here as you read through this. So we're told we have 55.5 liters of ammonia with excess oxygen. That's excess information, so we can ignore that. What mass of nitrogen monoxide will form? So we're taking information about the ammonia and relating it to the nitrogen monoxide. Let's think about what we're doing. We're starting with liters and we're going to grams. So we'll start with liters of our first substance. We'll use the 22.4 to convert it to moles. Then we'll use our mole ratio to relate between our two substances to get to moles of the second substance. And then we'll use the molar mass to get to grams of our second substance. So we will need 3 fractions. Here's your problem again. Again, I'm going to give you about a minute to work through this, and then we'll talk through how to work through this one. So I'll go ahead and open the poll here, and go ahead and start. Oh, we only have 1 vote in so far. But in terms of time, I want to make sure that we don't keep you much past 9 o'clock. So let's go ahead and look through our answer here and think about what we're doing. And we got 2 votes. Okay, awesome. So let's start to think through what we're doing. Maybe we're just punching in numbers at the end. So we go ahead and take our liters. First step is to convert it to moles using 1 mole over 22.4 liters. We'll then use our mole ratio to relate between the two. Now we're switching over to nitrogen monoxide. We don't want nitrogen monoxide. We don't want moles of nitrogen monoxide. We wanted grams. So then we'll use our molar mass, adding up the mass of a nitrogen and an oxygen, multiply across the top, divide by the bottom. We get an answer of 73.7. If we look back at our answer choices, that is in fact B, which are 2 votes that we got, and actually selected answer choice B. So fantastic job on working through that. Let me just scroll ahead a couple slides here, because we're going to skip over a couple slides, and we're going to move on to classroom materials. Now we do have some classroom materials. I'm going to pull up a pod that's going to share some information for resources you can use for stoichiometry. And again, I'll leave this up. So you've got some different information here you can use for stoichiometry, and I'll leave this up for you to download. So you've got a couple different activities that you can use. Some lab activities, limiting reagents, and a recipe is just kind of an intro that I use for baking cookies. To kind of get students thinking about stoichiometry with limiting reagents. Ice cream stoichiometry is always a fun one. And some practice and also some test review as well as a review PowerPoint. So I'm going to leave that up. The next thing I want to go ahead and pull up is a science survey. So to make sure that we get some information from you all about how we can best help you, if you would click on that link there, it is active on your screen. So if you would click on that, that should open in a separate window, I'm going to hope. And if you would go work through that and fill out that survey, that would give us some really important information to help us Science E-coaches know how we can best help you as students here in our sessions. So if you would click on that survey and fill that out, and I probably just about lost all of you, so hopefully just go ahead and open that in a separate browser window, and then you can come back and fill that out. In terms of wrapping things up, our next session for science is biology, which is next Wednesday. Science sessions are always on Wednesday nights. I'm going to pull up a couple extra pods here so you can get access to your files. So I've got our files here, so our files from earlier, the classroom resources for reactions. And I'll also share with you the PowerPoints from this evening session. So feel free to use any of these resources. And again, when you go to download those, you can download a whole group at once, but know it will open in a separate browser window in terms of accessing those. And as we're wrapping up here, there's one other thing I wanted to share with you. So I'm going to pull a different pod up.